Ask a neural network to solve one of physics' hardest problems, and it hits a wall you might not expect. To honor the equations of physics, these networks need to compute high-order derivatives, and they usually do it with automatic differentiation, the very same trick that trains them. But stack that operation again and again on noisy data, and the numbers blow up into instability. In 2026, a Penn Engineering team offered a fix drawn from 1940s mathematics. They call it Mollifier Layers. Let's unpack what it swaps out and why it matters. First, let's see the gap this technique is built to close. These networks lean on automatic differentiation to compute the derivatives that physics demands. For a high-order inverse problem, that means differentiating recursively again and again. On clean math, it works fine, but real measurements carry noise, and each pass of differentiation amplifies that noise further. The Penn team found the whole process turns unstable and computationally expensive exactly when the physics gets hard. Mollifier layers take a gentler route. Instead of differentiating a jagged signal directly, they first smooth it by convolving with a soft kernel, a mollifier, then measure the derivative of that smooth version. Kurt Otto Friedrichs introduced these smoothing functions back in the 1940s. Sliding one in front of the derivative tames the noise before it ever gets a chance to blow up. So how does a signal actually travel through this technique? Follow it one step at a time. Every inverse problem starts with messy, noisy data, the measured ripples you want to trace back to their cause. The old approach hands that raw signal straight to recursive automatic differentiation. Because differentiation reacts sharply to tiny wiggles, the noise gets magnified with every derivative, and a high-order equation demands many of them in a row. Here the mollifier layer steps in first. It convolves the noisy signal with a smooth kernel, averaging out the sharp wiggles while preserving the underlying shape. Think of gently blurring a photo, just enough that the real structure survives, but the random speckle fades away. The signal that emerges is now smooth enough to differentiate safely. Now, the network takes derivatives of that smooth signal. Because the input is no longer jagged, each successive derivative stays stable instead of exploding. The team reports this makes high-order derivatives tractable, where plain automatic differentiation would have amplified noise into nonsense, and it stays far cheaper as the order climbs. Finally, the model works backward to the hidden equation. With trustworthy derivatives in hand, it can infer the underlying partial differential equation that produced the data, the pebble behind the ripples. The Penn group used exactly this to study how cells organize their chromatin, and points toward fluid mechanics and weather forecasting too. Strip it back, and three ideas define mollifier layers. They swap an unstable operation for a smooth one. Rather than trusting recursive automatic differentiation on raw noisy data, they insert a smoothing convolution first. That single change turns a process that amplifies noise into one that suppresses it, which is precisely what unlocks reliable high-order derivatives. The idea borrows from mathematics, almost a century old. Kurt Otto Friedrichs defined mollifiers in the 1940s as a way to approximate rough functions with smooth ones. The Penn team, led by Vivek Shenoy, adapted that classical tool into a trainable neural network layer, published in Transactions on Machine Learning Research. They open up problems that were previously out of reach. Stable high-order derivatives let neural networks tackle inverse PDEs across science, from chromatin organization inside cells to materials, fluid mechanics, and weather. It is a targeted fix, not a universal solver, but it removes a very specific and painful bottleneck. All right, Let's lock in the essentials. Mollifier layers are a 2026 Penn Engineering technique that smooths a signal by convolution before taking derivatives, replacing unstable automatic differentiation with something far steadier. They exist because computing high-order derivatives with recursive automatic differentiation amplifies noise, turning unstable and expensive exactly when the physics gets hardest. By borrowing mollifiers from Friedrichs in the 1940s, they keep high-order derivatives stable, which lets networks solve inverse PDE problems more reliably. Remember, it is a smoothing layer, not a magic solver, but cracks a bottleneck that had blocked physics-informed networks for years. If you enjoy seeing fresh AI research explain this plainly, we have a whole library waiting for you over at standarity.com.